Welcome back to the lecture series in bioenergy. So, in the last class we talked about the different composition and the plants which should be selected or the algae which should be selected for biomass and subsequently for the biofuel production. So, today what we will do, we will systematically enumerate the features of those materials which could be used for biomass and bioenergy production. So, in parts here and there we have talked about them. We have talked about lignin versus cellulose ratio or cellulose to lignin ratio. We have talked a little bit about water. Now, we will talk in detail about it. And we have talked a little bit about alkali metals, presence of alkali metals and the problems what is being faced. So, now let us enumerate all the points. So, the way we will do is, we will first of all write down or jot down all the points or all the features which are essential, and then one by one we will pick up the factors and we will describe about them. And the basic understanding of these factors will eventually help you to understand which particular material will give what level of efficiency, while we will be converting it into some form of fuel or some form of energy. So, let us getting back to the slides. What are the factors or the material properties, whichever way we want to understand it, factors or slash material properties. Okay. So, the first and foremost thing is the moisture content, and we will talk in depth that what kind of moistures are there and how it influences our understanding and calculation, moisture content of the sample. Okay. Second thing, first of all, as we promised, that we will enumerate all the points. Next important thing is the calorific value. This is the next important thing, which in short also called as CV, calorific value. Then we have the proportion of fixed carbon versus the volatile in any sample. Proportion of fixed carbons versus the volatiles. Okay. Then there is a fourth factor which we call as ash slash residue content. How much ash is being produced, and these are all linked to the carbon level and the volatiles content. Okay. Fifth factor is alkali metal content, and here specifically we will talk about the role of silica, alkali metal content, and followed by the last important feature is what we have already discussed. We will be briefly try to pick up those points which we may have missed, cellulosic lignin ratio. Okay. So, these are the 6 critical features which eventually determines how much energy you can derive from the material. So, let us start with, let us get an understanding about this water content concept. What really water content is? So, there are 2 levels of water. One is called intrinsic water, the other one is called extrinsic water. Intrinsic water is that small amount of water or that internal water which is inherent in the material. In other words, the material is made up of proteins, carbohydrate, lipids. In between them there are lot of water molecules which wobbles around them, and it is the presence of the water molecule, that minimum amount of water, what helps these biomolecules to function. So, that is called the intrinsic water. So, let us getting back to the slide and let us start jotting down those points. So, now what we will be talking about is the water. Okay. Okay, moisture content or water content, okay. Moisture content. So, moisture content falls under two heading. The first one is intrinsic, the other one is extrinsic. In terms of the intrinsic, without the, so there is intrinsic water. If we talk about intrinsic water, has no influence from the weather condition. That much bare minimum of water is the bare essential for that biomolecule or for that system to function. Contrary to that, there is something called extrinsic water. Extrinsic water is the function of the environment. Say for example, you are harvesting a crop in the Kharif season or in the rainy season. So, in those seasons, the crops will have more water in them. Or when you have harvested the crop, there is a rainfall. They may pick up that moisture, and moisture plays a role in determining what kind of conversion strategy we have to follow. You must recall couple of lectures before, we talked about it, that there are certain plants, because of higher moisture content, they could only be processed by fermentation or biochemical route. Okay? Whereas at a lesser water content, you can use the direct heating technique or chemical degradation techniques, but that solely depends on the water content. Let's say for example, let's take up a case study. There is a lot of work happening across the world about algae. Now, algae grows in water, right? So, say for example, you have a population of algae which is growing there, which is oil producing algae. But now, you are pulling that algae out from water. It is rich in water. So, your first step comes, you have to remove the water as much as you can, and then only you can process it any further if you have to extract the oil out of it. But that process is not so easy. First of all, it needs a space. Second, it has its cost. Second, it needs energy, or you allow it to dry in the sun, but then you do not have any control on it. So, this is just one such example where if you have to remove that extrinsic, it is the extrinsic water, it is not the one which is present inside. It is because of the environment from where you are getting it, and that environment is either the sea, or it is a pond, or it's some river, right, some water body. So, that kind of water which is coming externally into the sample because of weather or because of the surrounding falls under this category, which is called extrinsic water. Okay? And so, this is basically either due to the weather. One route is weather, the second route is the surrounding environment. Surrounding environment. Okay. So, these are the two forms of water. Now, if you see a table, I will just draw a table for you as an example to understand this fact. So, before I put the table, there is something which I mentioned which I wanted to highlight here. So, say for example, you have a high moisture sample. So, this high moisture sample is generally suitable for any kind of conversion, is either through biochemical route or biochemical conversion route, or you could have fermentation route. Contrary to that, fermentation. Contrary to that, if you have a low moisture content, such sample goes through a thermal route. That does not mean that you cannot use a high moisture for thermal route. Of course, you can do so, but the energy consumption out here will be fairly high. Energy expenses will be prohibitive. In other words, you will have to spend a whole lot of more energy in order to transform a high moisture sample by a conversion route of thermal conversion route. Once we will come to all this classification of different conversion route, it will be clear to you, but just for your from your basic understanding you can kind of visualize that. It has more water and everything. You may love to go through a fermentation route where it converts into alcohol and so on and so forth. Okay. So, now coming back, so this is the energy expensive, which is a prohibitive route. Now, I was talking to you about the table. So, let us draw tables for your better understanding. Okay. So, you have the biomass. We put the columns, moisture, percentage, then the volatile material, which stands for VM, volatile material, and just put MAT for material. Then you have FC percentage. So, please get used to with this terminologies. It is called fixed carbon percentage. Then you have ash percentage, and then there is another terminology which will come in the next in the calorific value, which is called LHV percentage. LHV percentage is lower heating value. Lower heating value. We will come to that. What does that mean? What is the meaning of lower heating value? What is the fixed carbon and all those things? Lower heating value. Now, say for example, let us do a comparison, and this table will come very handy in the calorific value. If say for example, we compare between wood and wheat straw. So, what you will see is that in the wood essentially there will be 20% moisture, whereas in the wheat straw you will have 16% moisture. So, the first comparison. In terms of volatile mass, see the difference. 82% volatile material, whereas in the wheat you have only 59% volatile material. Contrary to it, fixed carbon here is 21%, whereas fixed carbon here is 17%. Okay? And the ash is 1%, whereas here ash is 4%, and lower heating value is 18.6%, whereas 17.3%. Just at this stage, do not worry about this part of the table. Just concentrate out here. This value is very critical, and this value, what is being reported in any literature, is intrinsic value. So, always remember these kind of tables, when they talk about the intrinsic value, they do not talk about the extrinsic value. Okay? So, that is the reason why I put that table in front of you. Now, coming back, so this is what all you needed to know about the water content. Okay? After the water content, we will talk about the calorific value, the phase 2 of it. Okay? So, this is the second parameter which is very important for us. Okay? So, coming back to the slide, so this is B, which is our calorific value. Okay, which is also, as I told you, denoted by CV, calorific value. So, calorific value is an expression of the energy content. It's an expression of the energy content or it is also a heat value, since it is in calorie, heat value released when burnt in air. When burnt in air. So, this is another part to remember when you are burning it in air. CV is usually measured is usually measured in terms of, now you remember in the very first class, the first phase of the lectures, I told you about all the units which will be essential in terms of the energy content, per unit mass, per unit mass. Okay, and or sometime or volume, because when you are calculating it for any kind of liquid. Hence, the unit is megajoule per kilogram for solid, joule per liter for liquids, and joule per Newton meter cube for gases. So, this is the unit which is being used, and CV can be expressed at two ways. There are two forms by which CV, just like water content, intrinsic and extrinsic, CV can be expressed in two processes. One is called gross calorific value, GCV, okay, GCV. The other one is called net CV, okay, NCV, which is also synonymous to gross, is also called higher heating value, higher heating value, which is HHV, higher heating value, whereas the net CV, calorific value, is also called lower. Now, you remember where this word came from, lower heating value, LHV. Now, what is the difference between the two? So, to explain you the difference, it is something like this. Whenever we calculate the calorific value, we take into account the latent heat of the water vapor. Say for example, what does that mean? Say for example, I have a sample, this is a sample, and I want to measure the calorific value of this stuff. So, there are a lot of water molecules inside it, right. So, if you remember, in the last class I was telling, what are we really deriving? We are deriving the breaking of the bonds between carbon, hydrogen, oxygen, likewise so on and so forth. Wherever there is a bond, we are breaking the bond. While we are breaking the bond, we are pulling two things apart. It is liberating an energy, and that is the energy what we are using, right. In order to do that, in that process what is happening? Say for example, there are two entities, say carbon, hydrogen. There are a lot of water molecules present in and around, right. So, when you are calculating the calorific value, those water molecules are getting evaporated. They are getting dissociated and getting evaporated. So, in other words, when you calculate the complete calorific value, you are calculating the latent heat of water vapor. But in real sense, that gives you an overestimation, and that complete picture of calorific value is what is, I have wrote here, is called higher heating value. So, in other words, if you have to define higher heating value, is the total energy, total, I am just putting E for energy, total energy content released when the fuel is burnt in air, when the fuel is burnt in air, including, now this is the important part, including the latent heat of water vapor. Now, latent heat, I am just putting as a triangle, of water vapor. Now, versus when we talk about the next one, which is lower heating value, what you are getting rid of in the lower heating value is this part. This is the part which is not included in the lower heating value. Okay. So, calorific value minus the is what makes it the lower heating value. So, essentially this is the more practical term, more practically used for all this kind of situation. Okay. Your LHV is equal to the CV, which is calculated for HHV, higher heating value, minus this value. Okay. And this is what is more practically used. So, wherever you see HHV, LHV, do not get confused, because it is a very simple concept. So, I believe this concept is clear to you. So, you are removing the water vapor, and then what you are getting is the real value. Now, if you see this table, now if you look at this table, so in this table you see there are two kinds of water which are present here, 20% moisture, 16% moisture, whereas LHV value is 18.6%, 18.6 and 17.3. Now, essentially what you have to do when you have to do this, you have to really proportionately reduce the heat or the value which will be generated while from the latent heat of this 20% moisture or 16% of this other product. So, in other words, 16% of the moisture value. So, whatever value you are getting, say for example, you are getting from here 18.6 minus the latent heat of 20% of water vapor. Similarly, 17.3% minus 16% of latent heat generated by 16% of water vapor. So, you see these calculations, whenever you see this kind of table, you should be able to proportionately make up in your mind that this is the amount which I have to deduct, otherwise I will get a superfluous value. So, what we see in this, there are 2 points what we have discussed as of now. The first point what we have discussed is about the water content. So, we talked about 2 forms of water content, intrinsic water, extrinsic water. Intrinsic water is the water which is embedded within the molecules in the core of that system, whereas extrinsic water is either from weather conditions or something you are getting out from water, or likewise that is external water which is getting into the system. And whenever the values are given, it is always the intrinsic value which is given. Next we talked about the calorific value. In the calorific value we talked about one gross calorific value, one net calorific value. So, gross calorific value takes into account the value which is including. So, sorry, I made one small mistake on the slide, sorry, just getting back to the slide. So, yeah. So, when we talk about the LHV value here, if it would have been, sorry, just this is one small correction. If it would have been HHV, then you have to remove this value. So this is in the LHV, so you really do not need to remove that proportion of moisture from it. Okay. So what we realize is that from the gross calorific value GCV, you have to remove the percentage latent heat given out by the water vapor. That value has to be reduced, and then what you get is the LHV value. So that was one small mistake I did, because I didn't keep an eye that that was an LHV value. So if it would have been an HHV value, high, or the gross calorific value, then what we have to do is that from the gross value you have to remove the latent heat of the water vapor. If you remove that, you get the net calorific value, which is also called LHV, okay, lower heat value. So these are the first two concepts. Next we will go after this to the other four concepts which are there, which will include the proportion of the fixed carbon versus the volatile. This will be the next one what we will be dealing with, followed by the ash residue content and the alkali metal, and we have already discussed part of it. Okay, so let's stop here. Thank you.